Hi, my name is Arya Gupta, and I am presenting the paper Analyzing Program Transitions to Compute Benefit of Tolerating Consistency Violation Faults. In this presentation, we'll discuss what are consistency violation faults, why they are bad, and why we want to tolerate them. In a general distributed system program, there are several processes, and every process has a set of variables. Every process stores a guarded command, several guarded commands, but for now, let's say that there is only one guarded command. G leads to A sub C, where G is the guard, and A sub C is the action which will be executed when the guard evaluates to true. Let's assume for now that process I is the only process of importance. So for example, graph coloring, process I will evaluate if there is some node k in the neighborhood of I, such that color of I is equal to color of k. And if that is so, I changes its color to some unused color in the neighborhood. A distributed systems program can be represented as a sequence of states, S0, S1, S2, and so on, where the transition from some state SL to state SL plus 1 is executed, is obtained by executing some guarded command in SL. Let's say that process I is the only process which is executing in SL, and since only one process is executing this, such an execution is called interleaving execution. There are other levels of concurrency, but for the sake of discussion in this presentation, let's only consider interleaving execution. Excuse me. Suppose that we have a program P that is correct with interleaving semantics. Now, how can we run this program when there are several processes running concurrently? One way is to run only one action at a time, but we don't want to do that. Another way is local mutual exclusion, where the processes ensure that when they are executing, their neighbors are not executing. This guarantees that execution can be serialized. There are other ways of implementing synchronization, but that depends on the kind of problem that we are dealing with. Local mutual exclusion ensures correctness in several levels, but it has a very high overhead. What happens if we do not use local mutual exclusion? Distributed systems community, including us, has told us that if we do not use local mutual exclusion, then bad things will happen. Let's see an example. Let's assume that there is a system of two processes. Process 1 has variable X and process 2 has variable Y. The actions are as follows. That process 1, if it sees that X is not equal to Y, it changes X and makes it equal to Y. In process 2, if it sees that Y is not equal to X, it changes Y and makes it equal to X. Now, if these actions are executed in an interleaving fashion, this is going to converge, and eventually X and Y are going to be equal to each other. But let's assume that P1 and P2 read the values of each other at the same time and perform the execution at the same time. In that case, X will be set to Y and Y will be set to X at the same time. And again, X and Y will not be equal to each other. And this can continue forever. Now, in practice, what happens? Now, in theory, we have seen that if we do not use proper synchronization, we are in trouble. Let's see what happens in practice if we allow asynchrony. Our group likes to call it living dangerously. In the following slides, we are going to study what consistency violation faults are and why we want to tolerate them. Recall that computation of a program is a sequence of states where the transition SL to SL plus 1 is obtained by executing action in one process. So we are considering interleaving execution. If we look microscopically into the sequence of states, what we will see is this. A global state such as S0 consists of several local states. Every local state is coming from some process. The variables stored in that process. Now, let's assume that for now that every process is storing only one variable. So process 1 is storing variable v1, process 2 is storing variable v2, and so on. So state 0 at time step 0, state S0 will be represented as v1 0, v2 0, v3 0, and so on. And state 1 at time step 1 will be represented at v1 1, v2 1, v3 1, and so on. And similarly, other states are represented similarly. Now, SL to SL plus 1 is supposed to appear like this. V11, V21, I'm sorry, V1L, V2L, V3L, and so on. And SL is V1L plus 1, V2L plus 1, and so on. When CVFs happen, so what CVFs are is when some process does not read fresh values, it reads values from the previous time step. It reads stale values, old values. So let's say that process I, again, is reading old values, and what it reads is not V1L, V2L, but it reads V1 alpha 1, V2 alpha 2, V3 alpha 3, and so on, where every alpha I is less than or equal to L. Now, based on what I reads, it is going to update its variables depending on what it reads. So there are two cases where the guard evaluates to false. In that case, there will be no change, and the new state, the resultant state, will be V1L, V2L, and so on, which is equal to SL. The second case is when G evaluates to true. Now, considering that only I is executing, all the other variables will not change, but VIL plus 1 is going to change. And it is going to change according to what I reads from its neighbors, which we know that they are not fresh values. What will happen with CVFs? Without additional constraints, we have seen that the program can go into deadlock, it can go into infinite loop, it can crash. So without additional constraints, eliminating CVFs is the only option. What happens when we allow CVFs in self-stabilizing programs? Recall that a self-stabilizing program a program is self-stabilizing with respect to the predicate P if it satisfies two conditions. If an action is executed in P, then the resultant state is also in P. And second, starting from any arbitrary state, every computation eventually reaches to a state in P. For now, so in the rest of the slides, we are only going to consider silent self-stabilizing algorithms, which means that once we reach P, none of the nodes are enabled, no actions are going to be executed. P, in this case, is called the invariant of the program. Wars between CVFs and self-stabilization. So there are some states which are satisfying P, and for those states, the rank will be 0. There are some states which are not satisfying P. For those states, the rank is greater than 0. In these two figures, assume that the blue states are in the invariant and the red states are not in the invariant, And both these graphs are the state transition diagrams, starting from state S. We have experimented two kinds of analysis. One is max rank and one is average rank. Max rank is the rank of a state, the longest path from a state, from an arbitrary state to one of the states in the invariant. So in this case, the longest path is 3, and therefore max rank S is equal to 3. Average rank, the second one is average rank, where we take all the paths, all the possible paths, and take their averages. So in this case, there are two paths, two possible paths, and the average is 2.5. A few observations. If the rate of CVF is very high, the program may not converge. If the rate of CVS is low, the program will probabilistically converge. But in that case, we do not need to address the cost that we have to give for synchronization requirements. We ran a few programs on several large graphs, and what we obtained is this. These are the readings which are coming, the first row are the readings which are coming from the synchronized programs. And the second row is coming from unsynchronized programs tolerating CVFs. So we can clearly see that the time required for unsynchronized programs we are getting is less than the programs that are running with synchronization. So allowing CVFs makes the program converge faster. Challenges in computing cost of CVFs. It's very difficult to compute CVFs of a given program. What we can compute are transient faults and feasible CVFs. Both of them are supersets of CVFs. Transient faults are can be explained with this example. Transition from S0 to S1, where S1 is obtained by changing state of one of the processes arbitrarily. In this case, average change in rank due to these transitions is 0. Feasible CVFs, they read arbitrary values from their neighbors, but they execute the associated action faithfully. So in this case, it can read wrong values, but if the guard values are true, the variable is only going to be incremented by 1. We have done 3 case studies: Dijkstra 3-token ring, graph coloring, and maximal matching. Our observations are as follows. The benefit of program transition has exponential distribution, where most program transitions reduce the rank by 1, and slightly less program transitions reduce the rank by 2, and so on. Cost of CVF transition has exponential distribution as well. Most CVF transitions increase the rank by 0. Slightly less CVF transitions increase the rank by 1, and so on. In this case, in our analysis, we ignore the CVFs that get us closer to the invariant. Observations for program or CVF benefit or cost. Here are some figures. And if we look at the right side of those figures, for example, in this figure, if we look at just the right side, all of them are logarithmic curves. So if we look at the right side here, we will see that the CVFs, they have an exponential distribution clearly. So the CVFs with very high costs are very infrequent, but very low cost CVFs are quite frequent. Relative cost of CVF. Relative CVF is a fraction which can be defined as follows. Average cost of CVF transitions divided by average benefit of program transitions. We have seen that a program can execute twice relative CVF transitions between a pair of CVFs. Convergence will be stable, but the number of steps, the number of steps may be twice as long. How many states to analyze? In this case, we have done 2 kinds of analysis: full analysis and partial analysis. In full analysis, we analyze the entire state space, and in partial analysis, we analyze a random subset of the state space. These are some figures which are showing max rank, average rank, partial analysis, full analysis for graph coloring, Dijkstra token ring, and maximal matching. And here we can see that the curves for max rank and average rank are fairly close to each other. Similarly, the curves for partial analysis and full analysis are close to each other. It means that in our analysis, we can rely on average rank analysis and the partial state space analysis as well, in place of max rank analysis and uh, full state space analysis. In this figure, we have, I'm sorry, in this slide, there are 3 figures. We have tried to experiment. We experimented the programs with different number of program transitions between a pair of CVFs, and we have seen that if the number of program transitions between a pair of CVFs is large, then the convergence will be faster. Similarly, in this figure, we took 100 random states and did the analysis, and we saw that we observed that if the number of program transitions between the CVFs is large, then the convergence will be faster. As conclusion, I want to make the following points. CVF tolerant systems have the potential to benefit from concurrency of the given system. Self-stabilizing programs automatically tolerate CVFs. An arbitrary program may not tolerate CVFs. Performance of stabilizing programs can be predicted analytically in the presence of CVFs. Ongoing or future work, we think that the following areas are very interesting to explore. Can we predict the expected performance based on probability distribution of program or CVF benefit or cost distribution, preferably analytically? How will probability distribution change with change in topology? Can we prove the probability distribution of program or CVF cost for a class of programs? This concludes my presentation. Thank you.